You think time exists. Of course you do. You can feel it passing right now. You remember yesterday. You anticipate tomorrow. Your watch is ticking. Your body is aging. Time is everywhere, always moving, always pushing you forward from the past into the future. It seems like the most obvious thing in the world. But here's what Richard Feynman would tell you. That feeling, that sensation of time flowing, that's not evidence that time exists. That's just your brain doing what brains do, creating a story out of patterns. And when you really dig into what time is, when you strip away the poetry and the intuition and look at what physics actually says, you discover something disturbing. Time might not be a thing at all. It might not exist in any meaningful sense. And if that breaks your brain, good, it should. Because the universe is under no obligation to match your feelings about it. Let's start with something Feynman insisted on repeatedly throughout his career. When you're trying to understand physics, you can't start with what feels right or what sounds beautiful. You have to start with what you can measure. This is what he called being operational. You don't ask what is time in some deep philosophical sense. You ask, how do we measure it? And the answer is surprisingly mundane. We measure time by counting periodic events. A pendulum swings back and forth, tick-tock. A quartz crystal vibrates. A cesium atom oscillates between energy states. We count the cycles, and we call that counting time. But notice what we're actually doing. We're not measuring time itself. We're measuring change. We're comparing one repeating process to another repeating process. You say your morning routine takes 30 minutes. What you really mean is that while you shower and dress and eat breakfast, your clock completes 30 cycles of its mechanism. That's it. That's the whole thing. There's no separate substance called time that's flowing past while you do these things. There's just change happening and us using one type of change to measure other types of change. Most people miss this completely. They think time is a container, an invisible framework that holds events. They imagine the universe is like a stage, and time is the backdrop against which everything happens. Even if you removed all the matter, all the energy, everything, they think time would still be there, ticking away in the empty void. This was Isaac Newton's view. He believed in what he called absolute time, a cosmic clock that ticks at the same rate everywhere, independent of anything happening in the universe. And for 200 years, that seemed obviously correct. But it's not correct. It's not even close. Albert Einstein destroyed that idea completely. And when you understand why, you start to see why Feynman could say with a straight face that time might not exist. Here's the problem Newton didn't know about. The speed of light is constant, always the same. No matter how fast you're moving, light always travels at the same speed relative to you. This shouldn't be possible. Speeds should add. If you're on a train moving forward and you throw a ball forward, the ball moves faster relative to the ground than it moves relative to you. But light doesn't do this. If you're on a train moving at half the speed of light and you shine a flashlight forward, the light doesn't move at 1.5 times the speed of light. It moves at the speed of light, exactly the same as if you were standing still. This is not a small technical detail. This is a complete violation of common sense. And when Einstein took this seriously, when he really worked through the mathematics of what it would mean for light to always travel at the same speed, he discovered that time cannot be absolute. Time must be flexible. Time must stretch and compress depending on how fast you're moving. Imagine you're sitting in a spaceship. You shine a light from the floor to the ceiling. From your perspective, the light goes straight up. But now imagine someone outside watching your spaceship fly past at high speed. From their perspective, the light doesn't go straight up. It goes at an angle, because while the light is traveling up, the ship is moving forward. So from their perspective, the light travels a longer distance. But here's the catch. Light must travel at the same speed for both of you. Same speed, longer distance, means only one thing: more time. From the outside observer's perspective, the light takes longer to reach the ceiling than it does from your perspective inside the ship. The same event, light traveling from floor to ceiling, takes different amounts of time depending on who's measuring. This isn't a measurement error. This isn't an illusion. Time actually passes at different rates for different observers depending on their relative motion. Your clock inside the ship is literally ticking slower from the perspective of someone watching you fly past. And if you could travel at close to the speed of light and then return to Earth, you would have aged less than everyone who stayed behind. This has been measured. It's been tested over and over. Atomic clocks on airplanes tick at different rates than atomic clocks on the ground. GPS satellites have to correct for this effect, or they'd be useless. Time is not a universal, absolute backdrop. Time is relative. It depends on your motion. But it gets stranger. Time also depends on gravity. The stronger the gravitational field you're in, the slower time passes for you relative to someone in a weaker field. If you stand at the base of a mountain for a day, you will have aged slightly less than someone who spent that day at the summit. The difference is tiny, unmeasurable without atomic clocks, but it's real. Time literally passes slower near massive objects. And if you could get close enough to a black hole, close to the event horizon, time would slow to a crawl from the perspective of someone far away. You could hover there for what feels like an hour, and when you flew back out, centuries would have passed for the rest of the universe. So here's the question that should be bothering you. If time can stretch and compress, if it can pass at different rates for different people, if it depends on where you are and how fast you're moving, then what is time? What is this thing that can bend and flex like rubber? And here's where Feynman's way of thinking becomes essential. He would say you're asking the wrong question. You're treating time like it's a substance, like it's made of something. But time isn't a substance. Time is a relationship. It's a way of organizing events, a bookkeeping system. It's not a thing that exists independently. It's a feature of how we describe the universe. Think about it this way. You have a photo album. The photos are arranged in order. This photo before that photo. That's all chronology is, a sequence, an ordering. The photos don't require a flowing substance called time to be in order. They're just arranged that way. Now imagine the universe is like a four-dimensional photo album. Every event that ever happens is like a photo in that album. And the structure of the album, the way the photos are ordered, that's what we call time. But there's no time flowing through the album. There's just structure. Just the spatial arrangement of events in a four-dimensional space. You move through that structure when you age, when you remember, when you anticipate, but the structure itself isn't moving, it just is. This is what physicists call the block universe. The past, present, and future all exist together as a four-dimensional structure. There's no flowing, no becoming, no passage. There's just the complete geometry of space-time laid out like a landscape. And you, your consciousness, you're like a train moving along tracks through that landscape. You experience the events in sequence because that's how consciousness works. But the tracks aren't moving, you are. Now, you might object. You might say, wait, that can't be right. I can feel time passing. Right now, this moment is now, and a second ago was the past. and a second from now is the future. That's not just a structure. That's real passage, real change. And Feynman would say, yes, you feel that. But what you're feeling is not time passing. What you're feeling is your brain's internal clock, a biological mechanism that evolved to help you navigate the world. Let me show you what he meant. Try this. Close your eyes and count to 60 seconds in your head. Try to be accurate. Most people can't do it. Some count too fast, some count too slow. And here's the interesting part. Different people use completely different methods. Some people hear a voice in their head saying the numbers. 1, 2, 3. For them, counting is auditory. If you interrupt them and make them speak out loud, they lose count because the speaking mechanism is tied up. But other people don't hear a voice at all. They see something. Maybe a ticker tape with numbers on it clicking past. Maybe a mental image of a clock face. For them, counting is visual. They can read a book or have a conversation while counting, because the visual system and the auditory system don't interfere with each other. This tells you something profound. Your internal sense of time, your feeling that time is passing, is just a mental trick, a pattern-matching algorithm running in your neurons. Different brains implement it differently, and none of it has anything to do with what time actually is in the universe. It's like asking, what color is Thursday? The question doesn't make sense. Thursday doesn't have a color. Color is a property your brain assigns to light wavelengths. Thursday is a position in a calendar, a label. Your brain might associate it with a color, but that's your brain's construction, not a property of time. Similarly, the feeling of time flowing is your brain's construction. It's not a property of the universe. Feynman was brutal about this. He said, if you want to understand time, you have to stop trusting your feelings and start trusting your measurements. And your measurements tell you that time is relative, flexible, and fundamentally just a coordinate, a way of labeling events in space-time. But let's go deeper, because there's another way in which time might not exist, and this one is even more radical. Feynman understood this from his work on quantum mechanics. At the deepest level of reality, at the scale of atoms and particles, time doesn't seem to play the same role it plays in our everyday experience. The equations of quantum mechanics are time-symmetric. That means if you run them forward, you get one answer, and if you run them backward, you get an equally valid answer. There's no built-in arrow. There's no direction. The past and future are treated identically by the mathematics. So why do we experience time as having a direction? Why can we remember the past but not the future? Why do eggs break but not spontaneously reassemble? The answer has nothing to do with time itself. It has to do with entropy, with disorder. The second law of thermodynamics says that in a closed system, entropy always increases. Systems naturally evolve from ordered states with fewer possible configurations to disordered states with many possible configurations. An unbroken egg is highly ordered. There's only one way to arrange the atoms to make that specific egg. But a broken egg, there are billions of ways to arrange the shattered shell, the splattered yolk, the scattered white. So when things interact randomly, they naturally evolve from order to disorder, simply because there are more ways to be disordered. This creates the appearance of an arrow of time. The direction of increasing entropy looks like time moving forward. But it's not time doing the work. It's just probability, just statistics. In principle, every interaction is reversible. The equations allow it. But in practice, reversing the breaking of an egg would require coordinating the motion of every single atom perfectly. And the odds of that happening by chance are so astronomically small that it never happens. So what we call the arrow of time, the feeling that the past is fixed and the future is open, that's not a property of time. That's a property of entropy, of how likely different configurations of matter are. Feynman emphasized this again and again. The laws of physics don't care about past or future. They work equally well in both directions. The only reason you perceive a direction is because you're a complex biological machine that evolved in a universe where entropy is increasing. Your brain records memories by creating ordered structures in neurons, and that process only works in the direction of increasing entropy. You can't remember the future because forming a memory increases entropy, and entropy only increases toward the future by definition. But that's your limitation, not time's property. Now we come to the most radical idea, and this is where things get truly strange. Some physicists, building on ideas that Feynman helped develop, argue that time might be an emergent property. That means time might not be fundamental at all. It might not be built into the basic structure of reality. Instead, time might emerge from something deeper, something more fundamental, in the same way that temperature emerges from the average motion of atoms. Temperature isn't a fundamental property. There's no temperature particle, no temperature field. Temperature is just a statistical description of how fast atoms are jiggling. It's a useful concept at large scales, but at the scale of individual atoms, it doesn't mean anything. What if time is the same? What if time is a large-scale statistical description of something else, something more fundamental that doesn't involve time at all? This idea is taken seriously in certain approaches to quantum gravity, the attempt to unify quantum mechanics and general relativity. In some versions of these theories, the fundamental equations don't have a time variable. There's no t. The universe, at its deepest level, is timeless. Instead, there are just relationships between different parts of the quantum state. And time emerges when you look at large-scale, low-entropy systems like our universe. Carlo Rovelli, a physicist who worked in the same intellectual tradition as Feynman, has pushed this idea hard. He argues that time is not fundamental. It's not part of the basic furniture of reality. Instead, time is an approximation that works well in certain situations, specifically in situations where entropy is low and you can define a clear direction of increasing disorder. In other situations, at the Planck scale, at the moment of the Big Bang, inside black holes, the concept of time might break down completely. It might not apply. And if that's true, then asking what happened before the Big Bang is meaningless. There is no before. Before is a time concept, and time doesn't exist at the Big Bang. It's like asking, what's north of the North Pole? The question seems grammatical, but it's actually nonsense, because direction breaks down at the pole. Similarly, time breaks down at the boundaries of the universe. This is disturbing. It violates everything you think you know about reality. But Feynman would say that's the point. The universe is not obligated to make sense to you. Your intuitions evolved to help you survive on the African savanna, to track predators and find food. They did not evolve to understand the fundamental structure of reality. So when your intuitions conflict with what the math and the measurements say, you don't trust your intuitions. You rebuild them. Let me show you how this works in practice. Consider what we mean when we say something exists. You say the table exists. What you mean is you can interact with it. You can touch it, see it, measure it. The table has effects on the world. It holds your coffee. It stops your hand from passing through. Existence means causal efficacy, the ability to affect things. Now ask, does time exist in that sense? Can time push on things? Can you interact with time directly? No, you can't touch time. You can't measure time itself. You can only measure change and use that change to define what you mean by time. Time is not an object. It's not a field. It's not a substance. It's a coordinate, a label, a way of organizing information about change. And in that sense, time doesn't exist the way tables exist. Time is more like the equator. The equator is useful. We can talk about crossing the equator. We can measure distances from the equator. But there's no physical line drawn on the Earth. The equator is a human invention, a coordinate system we impose on the planet to make navigation easier. Time might be the same, a coordinate system we impose on reality to make sense of change. Useful, yes. Essential for describing the world, yes. But not a thing in itself, not independently real. Feynman made this point in a different way when he talked about forces. He said people want to understand forces by reducing them to something more familiar, something mechanical. But you can't do that. Some forces are fundamental. They just are. There's no deeper explanation. You have to accept them as basic features of reality and build everything else on top of them. Time might be the opposite. It might feel fundamental, but actually it's built on top of other things. Built on change. Built on entropy. Built on the structure of space-time. And once you realize that, the question, why does time exist, becomes meaningless. Time doesn't exist in a way that requires explanation. Time is how we describe existence. It's the language we use, not the thing being described. This is hard to accept emotionally because time feels so real. You feel yourself aging. You feel moments slipping away. You feel the urgency of deadlines and the weight of regrets. Those feelings are real, but they're not evidence that time exists as a thing. They're evidence that you're a biological organism with a nervous system that evolved to navigate a changing environment. Your brain creates the sensation of time to help you survive. But that sensation, that subjective experience, is not the same as the physical reality. Think about color. When you see red, you're experiencing a sensation your brain creates in response to light of a certain wavelength. But the light itself isn't red. Redness is not a property of the photons. Redness is a property of your perceptual system. The photons have a wavelength, about 700 nanometers, and your brain interprets that wavelength as the color red. But to a bee, those same photons might create a completely different sensation, or no sensation at all. The redness exists in your head, not in the world. Time might be similar. The flowing, the becoming, the sense of now moving forward, those might all be properties of your perceptual system, not properties of the universe. The universe just is. It has a structure, a four-dimensional geometry, and your brain, navigating through that structure, creates the sensation of flow, the sensation of time passing. But the structure itself isn't flowing. It's static, eternal, timeless. This is the block universe again, but now you can see why it's so compelling. If time is relative, if it can stretch and compress, if it can pass at different rates for different observers, then there's no universal now. There's no single moment that is the present for everyone. Your now and my now are different if we're moving relative to each other. So what does it mean to say that one moment is now and another is the past? It's observer-dependent. It's subjective. And if it's subjective, then it's not a feature of reality itself. It's a feature of how we slice reality up, how we organize our experience. Feynman loved this kind of thinking. He loved stripping away the unnecessary baggage, the poetic language, the comforting stories we tell ourselves, and getting down to what the equations actually say. And the equations say that time is a coordinate in space-time. It's mixed together with space in a way that makes separating them arbitrary. You can rotate your coordinate system in space-time just like you can rotate your coordinate system in space. What you call time and what you call space depend on your choice of coordinates. That's not how things work if time is a fundamental, flowing entity. That's how things work if time is a label, a convention, a way of describing relationships between events. Now let's talk about what happens when you push this to the extreme. General relativity, Einstein's theory of gravity, describes how matter and energy curve space-time. The sun creates a dip in the fabric of space-time, and the Earth rolls around that dip. That's what we call an orbit. But here's the thing. In general relativity, the geometry of space-time is everything. There's no separate time variable that governs how things change. Instead, change is built into the geometry itself. The equations relate the shape of space-time at one place to the shape at another place. There's no external time ticking away. Time is part of the shape, part of the structure. When physicists try to combine general relativity with quantum mechanics, they run into a problem. In quantum mechanics, you have a wave function that evolves over time. Time is treated as an external parameter, something separate from the system. But in general relativity, time is part of the system. It's part of the geometry. So, when you try to write down a quantum theory of the whole universe, a theory of quantum gravity, you can't treat time as external anymore. You have to include it in the quantum description. And when you do that, something strange happens. The main equation of quantum gravity, the Wheeler-DeWitt equation, has no time variable. It describes the quantum state of the universe as static, timeless, unchanging. This is called the problem of time in quantum gravity. How do you recover the experience of time, the sensation of change, from a theory that has no time in it? The answer, according to some interpretations, is that time emerges. You don't put time into the theory. Time comes out of the theory as an approximation, as a way of describing certain patterns in the timeless quantum state. This is speculative. Quantum gravity is not a finished theory. We don't have experimental evidence for it yet. But the fact that our best attempts at unifying our two most successful theories, quantum mechanics and general relativity, both lead to timeless equations, that should tell you something. It should tell you that time, at the deepest level, might not be part of the picture. Feynman didn't work directly on quantum gravity. His contributions were in quantum field theory, in understanding how particles interact. But he understood the philosophy behind these ideas. He understood that when you're doing physics, you're building models. You're creating mathematical structures that describe patterns in nature. And sometimes, the things you thought were fundamental turn out to be emergent. Sometimes, the things you thought were emergent turn out to be fundamental. The only way to know is to follow the math, do the experiments, and see what works. And right now, the math is pointing toward time being emergent. Now, let's circle back to where we started. You feel time passing. You remember yesterday. You anticipate tomorrow. How do you reconcile that with the idea that time might not exist? Feynman would say you're confusing the map with the territory. Your experience of time is real. The sensation is real. But the sensation is not the thing itself. The sensation is your brain's way of modeling change, of organizing information, of navigating a universe where entropy is increasing. It's a useful fiction, an effective theory that works brilliantly at human scales. Just like Newtonian gravity is a useful fiction. It works brilliantly for launching satellites and building bridges. But at extreme scales, near black holes, at high speeds, it breaks down. You need general relativity. Similarly, classical notions of time work brilliantly for everyday life, but at extreme scales, near the Big Bang, inside black holes, at the Planck scale, they break down. You need a deeper theory. This is the pattern in physics. Every theory has a domain of validity. Within that domain, it works perfectly. Outside that domain, it fails, and you need something deeper. Newtonian mechanics works at low speeds. Relativity works at all speeds. Quantum mechanics works at small scales. Classical mechanics works at large scales. And time works when you're a low-entropy observer in a nearly classical universe, far from the Planck scale. But that doesn't mean time is fundamental. It means time is a damn good approximation. And there's a beauty in that. There's a beauty in realizing that the universe is simpler than it seems. That many of the things you thought were fundamental are actually derived. That the deep structure of reality is more elegant and more strange than you imagined. Feynman appreciated this. He appreciated the way understanding grows, the way you start with naive ideas and refine them, the way each generation of physicists peels back another layer and finds something unexpected underneath. And he had no patience for people who wanted to stop too early, who wanted to declare that time is just time and leave it at that. That's not understanding. That's giving up. So here's what Feynman explains. Time might not exist because what we call time is not a thing. It's a way of describing relationships between events. It's a coordinate, a bookkeeping device, a feature of how we carve up the four-dimensional structure of space-time. At human scales, in low-entropy environments, time emerges as a useful concept. It has an apparent direction because entropy increases. It has a rate because we compare one periodic process to another. But at the fundamental level, in the deepest equations of physics, time might not appear at all. The universe might simply be a static four-dimensional geometry, and your experience of time passing might be a consequence of how your consciousness navigates that geometry. This doesn't mean your life is an illusion. It doesn't mean nothing matters. It means reality is stranger than you thought. It means the flowing river of time that you feel so strongly, that seems so obvious, so undeniable, is actually a construct, a way your brain makes sense of change. And when you understand that, when you really internalize it, everything shifts. You stop asking why time flows and start asking why you perceive it that way. You stop treating time as a fundamental mystery and start treating it as an emergent property, something to be explained, not assumed. Feynman would say this is what science does. It takes the obvious and shows you it's not obvious. It takes the simple and shows you it's complicated. And then, if you're lucky, it finds something even simpler underneath. Time seems simple. Tick, tock, past, present, future. But when you look closely, it fragments into relativity, entropy, geometry, quantum mechanics, each piece more subtle than the last. And then, maybe, if we can solve quantum gravity, we'll find that underneath all that complexity is something beautifully simple. A timeless equation describing a timeless universe. And time, our dear familiar time, will turn out to be just a shadow, a projection, a way of talking about patterns in the timeless whole. That's not certain. Physics isn't finished. But it's where the evidence is pointing. And if it turns out to be true, if time really doesn't exist in the way you think it does, that won't diminish your experience. You'll still age. You'll still remember. You'll still plan for tomorrow. But you'll know, deep down, that those experiences are your brain's interpretation of something more fundamental. Something that doesn't care about past or future. Something that just is. And maybe that's the deepest lesson. The universe doesn't owe you intuitions that make sense. It doesn't owe you concepts that feel comfortable. What it offers instead is truth. Strange, beautiful, counterintuitive truth. And the price of that truth is giving up your comfortable illusions, your flowing rivers, and your universal nows. Feynman paid that price gladly. He looked at the equations, trusted the experiments, and followed where they led. And what he found was that time, that most fundamental seeming aspect of reality, might not be fundamental at all. It might be a useful fiction, an emergent approximation, a shadow on the wall of the cave. And recognizing that, accepting that, understanding that, that's not a loss. That's a gain. That's one more layer of reality revealed. That's one more step towards seeing the universe as it actually is, not as we wish it to be. That's physics. Not comfort, not familiarity, not confirmation of what you already believe. Truth. And the truth about time is that it might not exist. Not in the way you think it does. Not as a fundamental feature of reality, but as a description, a tool, a coordinate, a map we draw to navigate the timeless landscape of space-time. And once you see it that way, once you really see it, you can never unsee it. The river stops flowing, the now stops moving, and what's left is the eternal geometry of the universe, beautiful, strange, and indifferent to our need for time to be real. That's what Feynman explains. That's what the physics says. Time might not exist, and that's okay. The universe doesn't need time to be magnificent. It just is.